Trigonometry, Chapter 3, Radian Measure in the Unit Circle, Section 4, Linear and Angular Speed, Video 3, More Examples of Linear and Angular Speed. This series is based on content from Pearson's Trigonometry 12th edition by Lial, Hornsby, Schneider, and Daniels. In the previous video, we learned about the relationship between linear and angular speed. The equation was v equals r omega, where v is the linear speed of a point on the edge of a rotating circle, r is the radius of the circle, and omega is the angular speed of the circle in radians per unit time. In this video, we will look at two more examples involving linear and angular speed. For example, a satellite 1,600 kilometers above the Earth takes 2 hours to complete one orbit. 1. Calculate the linear speed of the satellite in kilometers per hour. And 2. Approximate the distance the satellite travels in 4.5 hours. First, we're going to calculate the linear speed of the satellite using v equals r times omega. Notice the radius of the satellite's path is not 1,600 kilometers. It's the height above the Earth plus the radius of the Earth. And since the radius of the Earth is illustrated as 6,400 kilometers, the radius of the satellite's orbit is 8,000 kilometers. Using a radius of 8,000 kilometers and an angular speed of omega equals one orbit in 2 hours, we have v equals 8,000 kilometers times one orbit per 2 hours. Now we convert orbits to radians for our unitless measurement. One orbit is like one revolution, so we multiply by 2 pi radians over one orbit. The orbits cancel, and we will be left with kilometers per hour because radians is unitless. And if we multiply, we get approximately 25,133 kilometers per hour. It is worth mentioning that back here, we could do something like this. We could say that the orbits cancel, the radians are gone, the 2 hours cancels with the 2, leaving 8,000 pi kilometers per hour. But when you're measuring things in real world situations, maybe you want something more like 25,133 kilometers per hour as opposed to 8,000 pi. But wait, we're not done. To find the distance traveled by the satellite in 4.5 hours, we simply use, let me get my laser pointer. Come on. We simply use speed equals distance divided by time, or solved for d, distance equals velocity times, distance equals speed times time. And since our speed was 25,133 kilometers per hour, then our distance is going to be that times 4.5 hours, which is approximately 113,098.5 kilometers. That's a long way to travel in just 4.5 hours. That's what I just said. All right, one more example. A belt runs a pulley of radius 6 centimeters at 80 RPMs. Find the speed of the belt in centimeters per second. Well, first, let's start with the linear speed of the belt. Well, that's what we're being asked, the speed of the belt. The linear speed of the belt is given by linear speed equals r times angular speed. Our radius is 6 centimeters, and our angular speed is 80 revolutions per minute, RPM. But remember, this only works if we are in radians, so we got to fix the revolutions. And we need seconds because we're being asked for centimeters per seconds, not centimeters per minutes. So we'll set up both conversions. The conversion to radians will be 2 pi radians per one revolution. And the conversion to seconds will be 1 minute to 60 seconds, and which works because the revolutions cancel, the minutes cancel, radians is unitless, and we're left with centimeters per second. And if we do the math, we end up getting about 50.3 centimeters per second. Now you try. Pause the video and try the following. The two pulleys in the figure have radii of 15 centimeters and 8 centimeters respectively. The larger pulley, not puller, pulley rotates 25 times in 36 seconds. The larger pulley rotates 25 times in 36 seconds. Find the angular speed of each pulley in radians per second. If you haven't paused the video yet, here's your warning. I am going to go through this solution instead of just show it to you. We start with the angular speed of the larger pulley. We know it rotates 25 revolutions in 36 seconds, so we set up that ratio. And to convert it to radians per second, we multiply by 2 pi radians per 1 revolution and get approximately 4.36 radians per second. To find the linear speed of the belt, well, we need the linear speed of the belt to find the angular speed of the other pulley. The reason is the second pulley, the only thing we know is its radius. We don't have any linear or angular speed. So we need to transfer the speed of the linear speed of the belt from the larger pulley to the smaller pulley. The linear speed of the belt from the larger pulley is speed equals the radius times the angular speed. So 15 centimeters times 4.3 radians per second. Again, radians is unitless, so that gives us 65.4 centimeters per second. Now we'll transfer that belt speed to the other pulley where the radius is only 8 centimeters. And then we use V equals R omega to get 65.4 centimeters per second equals 8 centimeters times omega. Then we solve this equation by dividing both sides by 8 centimeters, and we end up getting 8.175 radians per second. Technically, when you divide both sides of the equation by 8 centimeters, the centimeters cancel, and there are no units left on top. But remember, radians is a unitless measure. Not only can we remove it, we can reinsert it back into the ratio.